We constantly need energy, but we don't constantly eat, do we? I mean, some of you teenagers, you could potentially do that all the time, right? But as you get older, you have to slow down, or else you're going to get really large, right? So you don't constantly eat. Your body has a way of storing energy, right? Do you ever think about that? How does our body store energy? Do you guys know any of the energy storage molecules? You guys heard of any of those ones? Jen and I were just talking about one a few moments ago. Sugar.
Yeah,
right?
sugar.
Sugar is an energy storage molecule, and fat. Fat's a really good energy storage molecule as well. What were you saying, Jenna?
I think sugar might be the biggest storage molecule.
No, there's bigger ones, but it still carries a lot of energy, and that's a good thing for our bodies. Okay, so another molecule that you may not have heard about, because this is actually one of the smallest energy storage molecules, and that is ATP. Okay, so ATP stands for adenosine triphosphate. Let's go ahead and underline the A for adenosine, the T for tri, and then the P for phosphate. That's what ATP stands for. It's an abbreviation, adenosine triphosphate. And adenosine, if you look down at our diagram, this is a simplified structural formula for ATP. Adenosine is also known as adenine. Okay, so this part, this kind of peachish red part, is adenine. Another molecule that's part of ATP is the sugar part. So there's a little bit of sugar there. It's a 5-carbon sugar. That's why it's represented by a 5-sided shape there, a pentagon. But the most important part of ATP is over here on the right side, and that's where you'll find 1, 2, 3 phosphates. Let's number these. There's 1, 2, 3 phosphate groups. And these phosphate groups are all negatively charged. They all have a negative charge. Now, you have to think back. I bet you know a little bit about this, right? Things that are negative, do they attract other negative things, or do they negative things? Anybody remember anything about that? Maybe you've heard it said that opposites attract, right? Positive things are attracted to negative things.
Or do they what?
What? What'd you say, Brandon?
What?
Oh, I said that.
There for a second, Mr. Kramer.
Oh, I broke up. I'm sorry. My
Yeah.
bad. No, my internet connection's the problem here. I said that these phosphates are negatively charged. And do negative things attract each other or repel each other? They repel each other, right? They want to be as far apart as possible. Are they as far apart as possible in this molecule of ATP? No, right? They're all right next to each other, okay? And so these 3 phosphates with their negative charges, they all repel each other, right? That means they don't want to be anywhere near each other. But in this molecule, they're forced to be right next to each other. They're forced to be right next to each other. And so that makes these bonds really unstable, okay? These bonds right here, let's highlight those. This bond and this bond. Those bonds are holding back a tremendous amount of force. Those phosphate groups want to fly apart like a bullet from the gun. They just want to go bing, shoot apart. But those bonds are holding back all of that energy. Okay? So this is an unstable molecule. Let's go back up to the top here. It's an unstable molecule. What that means is it's ready to fall apart and release its energy. Okay? And so that's what we're seeing down here below. Let's look at the bottom of the page. You guys see that arrow there in the middle, right? That's a chemical reaction arrow. You guys remember what that means. Bonds are breaking, atoms are rearranging, new bonds are forming, right? In this case, we're going to break that bond right there. That bond right there gets broken. Okay? And so the result is it releases energy. How's my handwriting today? That says releases energy. Okay? Now here's an interesting thing about reactions. We didn't talk about this before, but chemical reactions oftentimes can be reversed, right? And so we can draw this arrow going to the left as well. It doesn't just go to the right, it goes to the left too. And so when we go to the left, we make that bond and we store energy. Does that make sense? So whenever we break the bond between the phosphates, we release the energy. And whenever we make that high energy bond, we store energy. So this is really important because this ATP molecule powers our enzymes. Let's write that at the bottom of the page here. ATP is like the gasoline that powers our enzyme tools. We thought about enzymes as tools because, just like tools, enzymes have a special shape, right? A hammer has a special shape that allows it to pound nails. A screwdriver has a special shape that allows it to screw in screws, right? Well, some enzymes are like power tools. They're like a chainsaw. Have you ever gotten to use a chainsaw? That's a scary tool. You can really hurt yourself if you're not careful. A chainsaw is a special tool. It's got a special shape, right? It's got a lot of pieces to it. There's a lot of parts to it, and it does a specialized job. But a chainsaw is worthless if you don't have any gasoline, right? You need gasoline in order to power that chainsaw. And so ATP acts like the gasoline for the enzyme molecules. It provides the energy by breaking and forming that bond between the phosphate groups. Okay, let's go one step farther, okay? Thanks for being patient. We just want to look at these two graphs down here. Graphs are a nice way to visualize how energy changes. Because energy, we can't see it, right? We can't see it, but we know it's there. It allows things to happen. It allows things to move and to do things. A graph allows us to see the energy change. And so let's look at this first graph. In the first graph, we're starting with low energy reactants. Let's put reactant over here. Remember, the reactant is what we start with. And we're ending up with high energy products over here. If I look at letter D, I draw a dotted line, right? The energy went up as this chemical reaction happened. So we store. And so in this chemical change, right, we started with low energy ADP, and we ended with high energy ATP. I guess I didn't explain. What do you think ADP stands for? What do you think that D is for? T stands for try. What do you think D stands for?
Die.
Die, right. And die is 2. If we scroll back up here, right, I didn't make a big deal of this. I should have. This molecule on the left we know is ATP. This molecule on the right is ADP. Do you see how it has 2 phosphate groups? Not 3. And so therefore ADP has less high energy bonds and therefore less energy. Okay? This next reaction is just the opposite. Actually, before we go any farther, let's make sure we say ADP plus P, that stands for a phosphate, forms ATP. That's the chemical reaction that graph represents. We started with something low energy, and we ended up with something high energy. If we want to jot down low before, high later. And remember, when we do that, we store energy. So when we go from low to high, we store energy in a highly unstable bond. Okay? Let's look at the second graph. The second graph's just the opposite in every way. So instead of starting with ADP, we're starting with something that's high in energy. That's ATP. And after the chemical reaction, we end up with something lower in energy, ADP. Let's go ahead and draw a dotted line to the y-axis here. The energy went down. I guess we should also label reactants, right? ATP is the reactant on this one, and ADP is the product on this one. So let's write the chemical change for this one. We started with ATP. Remember, ATP is our high energy molecule. And we ended up with ADP, which is low energy. And so when we go from high to low, are we storing energy or releasing energy?
Releasing.
You got it. We're releasing the energy. That's so that our bodies can live, right? If we store the energy, we can have the energy later. If we release the energy, we can use it, right? And this allows us to constantly have the ability to keep our head up and to allow our heart to beat and our brain to function. All these things wouldn't happen unless we had energy. Okay, that's everything for today. Let's just summarize, okay? We said that there's a high energy molecule called ATP. ATP stores energy in these unstable bonds. That energy gets released when we make ADP, which is adenosine diphosphate, and it's stored when we make ATP, which is high energy with 3 phosphates. Okay? We think of ATP as like the gasoline. It's the gasoline that powers our enzyme tools. So we think of enzymes as not just mechanical tools, but power tools. They require energy. And so there's 2 chemical reactions here. When we make ATP, that's the first graph, we store energy. When we break down ATP into ADP, we release energy. Do you guys have any questions? Mrs. Perscal, are we okay in the classroom?